In this video, we're going to start Chapter 9, talking about monoprotic acid and base equilibrium. So your textbook author, starts this chapter by saying that acids and bases are really essential to virtually every application of chemistry, and also for the intelligent use of analytical chemistry procedures like chromatography and electrophoresis that you might encounter in your work. So Chapter 9 is all about monoprotic acids and bases, where we have one proton that could be donated or accepted. Chapter 10, we get into polyprotic acids and bases. So just as a reminder or a note, nearly every biological micromolecule that you're going to encounter is probably some sort of polyprotic acid or base, or at least they have some of those properties. So this is really a hugely important branch of chemistry. And so we're going to think about how we can apply equilibria to all of this and start thinking about what all is going on in solutions. Let's look at strong acids and bases. So just as a reminder, strong acids and bases are strong electrolytes. And remember what that means. That means it's something that when it gets added to water, completely dissociates into its ions, at least essentially completely dissociates. So for an acid, for example, this means this reaction, right? So we've got some acid here, HA. It's a monoprotic acid, so this H that's represented here, that's the acidic proton, the one that can be donated to water in this case. A just represents the rest of the acid molecule, whatever atoms make up the rest of that molecule. So this is dissolved in water. We can imagine that a proton gets transferred over essentially 100%. So all of the molecules that have a proton attached are going to donate one to water. And so we end up with essentially 100% of the moles of HA being converted to hydronium and A-. So oftentimes we will more simply write this reaction as just HA dissociating to give us H plus and A minus. That just simplifies how the equation looks a little bit. So there we go. So as we've talked about in Chapter 6, you might remember, this reaction has an equilibrium constant called the acid dissociation constant. So we're assuming that this reaction is, at least in principle, reversible, although if it's a strong acid, it's essentially irreversible. So that acid dissociation constant, we call that Ka, and it's products over reactants, right? So the hydronium ion concentration times the A- concentration. A- would be the conjugate base of the acid HA, and then we divide by the concentration of HA. So if this is a strong acid, then our Ka value is going to be greater than 1. And typically it's going to be much, much greater than 1, indicated here by the 2 greater than symbols. So how do you know if you encounter a strong acid or base? Well, we probably want to use this table. So this lists the common strong acids and bases. So these aren't all of them, but these are mostly the ones that you're going to be likely to bump into in a typical chemistry laboratory. So there are just 6 strong acids that you kind of need to memorize. So do memorize these. So if we go down that next to the last column of the periodic table, so not the noble gases, but the halogens, and we start at the top, so fluorine doesn't count, but then going on down, chlorine, bromine, iodine are all in a row here. So as acids, this is hydrochloric acid, hydrobromic acid, and hydroiodic acid. And so these are all strong acids. Then we have H2SO4, sulfuric acid. There's a little footnote here that reminds us that for H2SO4, only the first proton is a strong acid. So for example, only one of these 2 H pluses that could comes off in a strong manner. So 100% dissociation for the first proton. The other one, well, takes a little bit more work. It's kind of a weak acid. Then we have nitric acid, HNO3, and perchloric acid, HClO4. So for bases, lithium hydroxide, sodium hydroxide, potassium, rubidium, and cesium hydroxide, so all of these guys. And so these are just the alkali metals going down that first column, group 1 of the periodic table. So those metal hydroxide, alkali metal hydroxides are all strong common bases. Another common base that you might encounter is this. This one's a little bit more complicated that you might discover in organic chemistry. This is called a quaternary ammonium hydroxide. And there's a little footnote here that this is a general formula for any hydroxide salt of an ammonium cation containing 4 organic groups. So let's make that a little more clear by drawing out some structures here. Okay, so basically we have nitrogen here as the central atom, and it's going to make 4 single bonds to things. And when it does, it's going to give itself a positive formal charge there. And then we're going to have these 4 different groups that we're going to label by R. And R can be basically any organic group. And then, because this has a positive charge, we can imagine that this ion attaches itself to a hydroxide. So here's the Lewis dot structure for a hydroxide, and this has a negative charge. So it's the plus likes minus. Going on here that causes it's the plus likes minus that causes there to be an attraction here, and that's why this is a salt, because we've got an ionic compound, right? So there's an ionic bond between these 2 ions. So what are some examples of these R groups? Well, maybe simply they could be methyl groups. So if we draw out the structure again, maybe these are CH3 groups. So typically these will be any group that contain carbon, hydrogen, and maybe some other atoms, but typically just carbon and hydrogen. So these are all methyl groups here. And so this would be tetramethylammonium. That's the name for this ion. And then we would say it's hydroxide, tetramethylammonium hydroxide. And so these guys are strong bases. So these ions, when you put them in water, will completely dissociate and give you hydroxide ions floating around. So they're strong bases. Okay, so one thing that we would like to be able to do with strong bases is to be able to calculate the pH. And we might also want to know the concentrations of, say, the acid or the conjugate base. So we might need some of those things. So for practical concentrations that you'll typically encounter in a lab, so that means concentrations that are greater than about 10 to the minus 6 molar, we can get pH or even pOH directly from the formal concentration of the acid or base. So here's an example problem. What is the pH of a 1.5 times 10 to the minus 3rd molar hydrochloric acid solution? So since we're above this 10 to the minus 6, we can get pH sort of directly. So since this is a strong acid, hydrochloric acid, it's going to dissociate 100% into H plus and Cl minus. So if we have 1.5 times 10 to the minus 3rd moles of HCl, when it dissociates, we're going to get 1.5 times 10 to the negative 3rd moles of H plus and the same number of moles of Cl minus. So then we know that our H plus ion concentration is 1.5 times 10 to the negative 3rd. So how do we find the pH of that solution? Ignoring activity coefficients, we're going to use our definition that pH is equal to the negative log of the H plus ion concentration. So we just plug that in there and we get our pH. What if we wanted to find pOH? Well, for that we can use this helpful equation that's down here in the blue box. So this tells us that pH plus pOH is equal to the negative log of Kw. Sometimes we will call this pKw. And at 25 degrees Celsius, that happens to equal 14. So since we've just calculated the pH, 2.82, we don't know the pOH yet, but we know when you add them together, they have to equal 14, as long as we're at 25 degrees Celsius. Then you just solve the algebra in this equation for pOH, and we come up with a pOH of 11.18. So we can find both the pH and the pOH and the concentration of chloride, if we actually wanted to know that, for our species that are in the solution. So let's look at this example. So let's say we wanted to include the activity coefficient. So this is an example from your textbook, and we want to know what's the pH of 0.1 molar HBr. So because we've memorized it, we know that HBr is a strong acid, so it's going to essentially 100% dissociate. So that's going to give us 1 mole of 0.1 moles per liter of H plus and 0.1 moles per liter of Br minus. And so that's a 1-to-1 electrolyte, and we know the shortcut here, that gives us an ionic strength of 0.1 molar. So we look up the activity coefficient from the table in Chapter 8, Table 8-1, and we figure out that the gamma value for H plus is 0.83. So now we need to remember that with this fancier definition, closer to what a pH meter would actually measure, that the pH is equal to the negative log of the hydrogen ion activity. And so we take the negative log of the hydrogen ion concentration, right? So activity is concentration times the activity coefficient. Our concentration is 0.1 molar for the H plus, 100% dissociation. Then our activity coefficient is 0.83, and so we would get a pH of 1.08. Now, if you work this problem without activities, we would get a pH using our other definition, negative log of 0.1. We would get a pH of 1, right? So we're not that much different, but in cases where we need to do precise work, maybe we do care about pH changes that are out here in the hundredths place, and we would need to include the activity coefficient. So here's a problem that you can pause the video and work yourself to see if you can get the correct answer. you can go to your textbook to check and see that you get the correct answer. So what'll be a little bit different from this problem is that we have an extra source here of ions, and so you'll need to include the 0.09 molar potassium bromide in your ionic strength calculation. So let's check out this problem. So what would be the pH of a 1.0 times 10 to the molar sodium hydroxide solution at 25 degrees Celsius? So sodium hydroxide is a strong base, so we know that it's going to completely dissociate to give us sodium cations and hydroxide anions. And so each of these is going to have a concentration then of 10 to the minus 8th molar. So you might just say, oh, well, I know exactly what to do. I'm going to find the pOH as the negative log of the hydroxide ion concentration. And that's going to give me take the negative log of 10 to the minus 8th. The log just brings down the power on the power of 10, and then we multiply by the minus 1. And so we're going to get a pOH of 8. And then we can figure out the pH, because pH is 14 minus the pOH, which is 8. And so 14 minus 8 is going to give us a pH of 6. Now, if you think about that a little bit, you'll realize that that's kind of surprising, right? Because sodium hydroxide is a base, and yet we're getting an acidic pH. So that can't be right. Something must have gone wrong. So that's right. It cannot be a pH of 6. It should be basic. A solution with a pH perhaps only a little bit higher, but a little bit higher than 7. So what do we need to do to solve this problem? Well, there's two reactions that are important. The first one happens 100%, right? We go to completion, the sodium hydroxide breaks up into sodium plus and hydroxide. But the other reaction that we have going on, because this is water, is the autoprotolysis reaction. So water is going to break up a little bit to give us H plus and OH minus. So reaction number 1 is not our only source of hydroxide. And since our hydroxide ion concentration is so small, we might need to consider the hydroxide ion concentration that we get from the dissociation of water. So we're going to use the systematic treatment of equilibrium, but we are going to ignore, use the systematic treatment of equilibrium, but we are going to ignore activity effects. So this bit right here, this is going to be our formal concentration. So before anything is dissociated, right, it's 100% dissociation, but so there is actually no sodium hydroxide in our solution at all, right? So the sodiums and hydroxides have completely separated. So I'm just going to call this 1.0 times 10 to the minus 8th molar the formal concentration. I'm going to give that the symbol F. All right, so systematic treatment of equilibrium, we need to write down our pertinent reactions. So there they are. Then we need to write down our charge balance and mass balance equation. So we're going to start off with the mass balance equation, so MB here. So what is that? Well, really there are two sources of hydroxide, so I don't have a mass balance for that, but I do know that all of the sodium in this solution has to come from the formal concentration that we added at the beginning. So my mass balance equation is going to tell me that the formal concentration is going to be equal to the equilibrium sodium cation concentration. So there's my mass balance. Now let's do charge balance. So what things do I have in my solution that are positive? I have sodium cations. So I need to know the molarity of that. Then I also have hydrogen ions from the water autoionization, this reaction up here. So those are my positively charged things. And the only negatively charged thing I have is hydroxide. So there's my charge balance equation. Then I've got 3 unknown concentrations here, sodium, hydrogen, and OH minus, so I need another reaction, another equation, and so that's going to be my water autoionization reaction. So Kw is equal to H plus times OH minus. So now I've got 3 equations in 3 unknowns, counting everything up, so I'm good to go to try and use algebra to solve this. So remember how the algebra goes. We're going to substitute for things and try and eliminate variables. So first thing that I'm going to do is for the sodium cation, I'm going to replace the sodium cation with F, right? So I get this as sort of my first replacement. So F is, F plus the concentration of H plus is equal to the concentration of OH minus. So now in this equation, I've just got 2 unknowns. And so then as a last step, I can substitute for OH minus into the Kw equation. So Kw is going to be equal to the H plus concentration times the OH minus concentration. But what is the OH minus concentration? It's F plus H plus. And so I can multiply the H plus inside the parentheses here, distribute that, and we get F times H plus H plus squared, right? So these are just like algebraic variables there, and that all equals KW. So rearranging this equation a little bit, I can subtract KW from both sides of this equation, and I can get this equation. So H plus squared plus F times the H plus ion concentration minus KW equals 0. So now I've got one equation and one unknown. And if you stare at this equation, you might notice that it has this kind of familiar form. Some constant A times x squared plus some constant B, in this case that happens to be F, right? We know what that is, that's this number up here, times X, if we're letting X be the H plus ion concentration, plus C equals 0. So C is another constant, and in this case, our C is just minus KW. And so our B is F, and our A would be 1, because 1 is multiplying H plus here. And so you'll recognize this. This is the quadratic equation. And so now hopefully you're having visions of your high school algebra teacher grinning sinisterly at you, reminding you that you might see this again. Yes, and here we go. So in order to solve this equation, we need the solution of the quadratic equation, right? So x is equal to negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. And so knowing what a, b, and c are, we just identified those here. You can plug them into the equation and solve for x. Now, depending on the plus or the minus, you're going to get two different roots for this equation. One of them is not going to make sense. So remember, x is supposed to be the hydrogen ion concentration. And so if you get a negative number for concentration, negative molarity, what does that mean? Yeah, that's nonsense. So we can't have negative molarities. So if you happen to get a negative number, we're going to discard that solution. So you can plug numbers in here. I like to, when I'm working problems not on a test or something, go into the web and find a quadratic equation solver. So you can just type in the values of a, b, and c, and it'll spit out the two roots. So in this case, when you solve this, the positive root is 9.51 times 10 to the minus 8. And we will remember that that's a molarity, right? And so x is what? X is our H plus ion concentration. That's how we defined it from our equation right here, right? So now we just need to take the negative log of that number. So the negative log of that number is going to be the pH, and that gives us a pH of 7.02. So using the systematic treatment of equilibrium, we can solve this, and we see that, lo and behold, we do have a pH that is ever so slightly basic, right? 7.02 is a little bit different from 7.00, so we're ever so slightly basic, as we might expect for a base that has this tiny, tiny concentration. So here's the upshot of that little bit about calculating the pH of strong acid or base solutions. So when the concentration is kind of near 10 to the minus 7th molar, you need to use the systematic treatment of equilibrium to calculate the pH. If you're higher than that, then you can use just the concentration, the formal concentration of the acid or base to calculate the pH, because the systematic treatment of equilibrium will change that barely at all, so we don't need to worry about that. And then at still lower concentrations, so if you're lower than about, say, 10 to the power minus 8, down here, then you can just say that the pH is 7, and that's controlled by the autoprotolysis of the water. So this is our little graph that tells us what we need to do. So in this region, we can use just the formal concentration. Here we need to do that fancy systematic treatment of equilibrium that I just did, and past 10 to the minus 8 molar, we just say it's 7. So what about weak acids and bases? So now we're going to be talking about this equilibrium reaction. So this is the acid dissociation reaction of a weak acid in water. So it's an acid, it's going to donate its proton to a base, water in this case, and make hydronium an A-. Again, sometimes we will simplify writing that by just saying HA in equilibrium with H plus A-. So this is showing you the dissociation reaction. And as a weak acid, right, this is an equilibrium. We can write down the equilibrium constant that we call Ka, the acid dissociation constant. And it's the concentration of H plus times the concentration of A-. A-, you'll remember, is the conjugate base, of this weak acid, and then we divide it by the HA concentration. So to be a weak acid then, what happens? Well, you have to have Ka's less than 1. So how do you recognize weak acids? Well, weak acids are any acid that is not a strong acid, and we memorize those 6 common strong acids. It's probably safe to assume that most other acids that you encounter are going to be weak. But if you go back to chapter 6, you'll remember that we talked about some common weak acids. So they were things like carboxylic acids that you learn about in organic chemistry. Also, the ammonium cation, NH4+, is a weak acid, and things related to it. So for weak bases, then we have a base hydrolysis. So the bases are proton takers. They're going to take a proton from water. There's an equilibrium where you have the protonated base, BH+, and hydroxide. And so we have a base hydrolysis constant, Kb here, and it has this form, right? So products over reactants, it's the protonated BH+ times the hydroxide concentration divided by the unreacted base concentration. And again, to be a weak base, we expect that the Kb value is going to be something less than 1. So sometimes we will talk about pK values. So P, remember, is just the negative log of whatever comes after it. So pKw is the negative log of Kw. pKa is the negative log of Ka, and pKb is the negative log of Kb. So sometimes we will talk about the pKa of a weak acid. And just a reminder that when we're looking at these negative logs, we're sort of looking at the exponents on the Ka value. So larger pKs mean weaker acids or bases. So if you have a pKa of 3 versus a pKa of 12, the one that has the pKa of 12 is a much weaker acid than the one that has a pKa of 3. So just keep that in mind. Now for conjugate acid-base pairs, right? So HA is a weak acid, A- would be a weak base, so it would have a base hydrolysis reaction. We can imagine the A- taking a proton from water to give you these things, the HA recreated, and then the OH-. So if you have conjugate acid-base pairs, we looked at this in chapter 6, that when you multiply the equilibrium constants together, you get H+ times OH-, which is the equilibrium constant for Kw. So this is a very important, useful relationship, but it only works for conjugate acid-base pairs. So make sure you're talking about a conjugate acid-base pair, which we learned about, just as a reminder, back in chapter 6. So you might review your notes there. So the relationship is this. The Ka for the weak acid is equal to the Kb for its conjugate base hydrolysis reaction. You multiply those together, you get Kw. So how is this useful? If you know one, you can find the other. We have a table in the back of our book, Appendix G, and you can go look up Ka values for a bunch of different acids. But sometimes you might want to know the Kb value for a base. Well, you look up the Ka value for its conjugate acid, and then you use this equation to find the Kb value. So we would just divide both sides by Ka, and you would get that Kb is equal to Kw divided by Ka. We know what Kw is. It's 1 times 10 to the minus 14, as long as we're at 25 degrees Celsius, an important thing to remember. If we wanted to, we could take the negative log of both sides of this equation and rewrite it like this. And then we have it in terms of pKa's and pKb's. So the pKa plus the pKb will always equal pKw, which at 25 degrees Celsius is 14. So these are some useful relationships. So a couple of notes. So Harris talks about, remember, weak is conjugate to weak. So the conjugate base of a weak acid is in fact a base and behaves like a base in solution, but it is a weak base. So that's what it means that weak is conjugate to weak. Similarly, the conjugate acid of a weak base is also a weak acid. So how is that? Well, we have an inverse relationship between strength of conjugate acids and bases. So looking at this equation, I've solved this equation for Kb right here. And so you see we have an inverse relationship because we've got this Ka in the denominator. So as Ka gets big, Kb gets small. That's what we mean by an inverse relationship. So it is true that as HA becomes a weaker and weaker acid, that the conjugate base, A-, becomes a stronger and stronger base. So even though it is becoming stronger and stronger, it is nonetheless still a weak base. So that's what we mean that weak is conjugate to weak. We will still have a weak base. A minus will be a weak base. But it is true we have this inverse relationship. So the stronger the acid, the weaker the base. That kind of thing is going on. What if we have a strong acid like HCl? Well, what would its conjugate base be? Well, its conjugate base is chloride. That's what you get when you pop off an H+. So this conjugate base is so weak, right? The Kb, the Ka is so large that the Kb is going to be a tiny number. So it is so weak that it's not a base at all in water. It does not behave like a base at all in water. So we can ignore its acid-base properties. So as I mentioned, we can go and look up acid dissociation constants or calculate base dissociation constants by using a table in the back of our book. So in the back of your book, Appendix G lists acid dissociation constants for a bunch of different acids. So I wanted to talk a little bit about how to use this table. So first off, the table shows only the fully protonated form. So this is always going to show you the conjugate acid form. So if you're looking up a base, you need to look for its conjugate acid. The name that they give in this column is for the neutral molecule. So that'll be the molecule that has no net charge. So even though what is pictured in the structure might have a charge, the name is for the one with no net charge. And so what's shown in the table is the name, then it has the structure, and then it highlights in blue the acidic protons. And then here, we're assuming that ionic strength is equal to 0, so we are ignoring activity effects, and that's what these two columns are. The first column is just the pKa value. The second column is the corresponding Ka value. Now, if we were at an ionic strength of 0.1 molar, then what's reported here is the pKa that you would have accounting for the activity coefficient effects. So basically what we're doing is taking those activity coefficients and putting them inside the Ka, and this would be the value. So typically we're going to use these first two columns. If you're looking up Ka values, use this middle column. So in some cases, you will see that there are polyprotic acids where you have more than one ionizable proton. So for example, the amino acid alanine, you can ionize both the carboxylic acid, H off that molecule, and also the H that's attached to this NH3 plus group, the ammonium group. And so it lists sort of next to the structure what the Ka is. So this first proton, the ammonium proton, has a Ka of 4.53 times 10 to the negative third. It is the stronger acid compared to this one. So the carboxylic acid down here, this H+, has a Ka value of 1.36 times 10 to the negative 10th. So it comes off less easily than this first proton does. So you'll always have, for polyprotic acids, multiple Ka values that you can look up here. All right, so moving on, let's think about, since we've already talked about how we calculate pH and pOH and concentrations for strong acids and bases, how do we do that same thing for weak acids or weak bases? So we want to be able to calculate the concentrations at equilibrium of all the species that might be in our solution, as well as the pH and the pOH. So typically we will be given a formal concentration, which again, I'm going to use a symbol F for formal concentration. And we usually express concentration in units of molarity. And that will be for the weak acid. So we know that the weak acid, some of it is going to dissociate, so we actually don't have the formal concentration of acid in our solution, right? That's the concentration before anything dissociates. So how do we work this problem? Well, we're going to use the systematic treatment of equilibrium. First off, because that's always the right thing to do, and hopefully we won't have to do the ugliness of all the systematic treatment of equilibrium. Maybe we can find some approximations on the way that will help us out. So first off, we write down our pertinent reactions. So here they are, the weak acid dissociation reaction and the autoprotolysis of water. Then we're going to write down our charge balance. So the only positively charged thing that we have here is hydronium. Negative charges are our conjugate base, A-, and hydroxides. There's charge balance. So mass balance, F. So the formal concentration of our HA, A can go two places. One, it can be the conjugate base, but it can also be undissociated acid. It can also exist in undissociated acid. So when we add these two molarities together at equilibrium, they should equal our formal concentration. So there's our mass balance expression. Then we can write two other equations for our equilibrium constants for our two reactions up here, the acid dissociation and water hydrolysis reactions. So here we go. And so if you count all the unknowns, H plus, A minus, OH minus, and HA, we have 4, and we have 4 equations, charge balance, mass balance, Ka and Kw. So now we're ready to try and do the systematic treatment of equilibrium. If you try to do that, you'll discover that you can do it, but it gets pretty messy. We end up with an equation that has H plus raised to the third power. So we call that a cubic equation. Now there are equations like the quadratic equation to solve the cubic equation under certain conditions, but it's messy and it's hard, right? So we would like an easier way of solving these problems. So just when we're about to give up, the good chemist, as your textbook author says, comes galloping down from the mountain on her white stallion and cries to us, "Wait! There's no reason to solve a quadratic equation. We can make some excellent simplifying assumptions." And here's what those simplifying assumptions are. So if this is a weak acid at all, it's going to make the H plus concentration. It's going to give us some H plus concentration and also some A minus concentration. So since we're going to have a relatively high H plus concentration, remember that because of this reaction, the H plus concentration is going to shift this equilibrium this direction according to Le Chatelier's principle. So that means our OH minus concentration is going to be really small. And so for any weak acid, Harris says, worth its salt, you're going to have an A minus concentration that is much greater than the OH minus concentration. So looking at our charge balance equation here on the right-hand side, we can essentially say this, that our H plus concentration is going to be approximately equal to, so that's what the wiggly equal sign means, approximately equal to A minus. And that's because the hydroxide ion concentration, we expect that's going to be really small. Because we will have dissociated some of our acid, we made some H+, that's going to shift this equilibrium back this direction. The OH minus concentration in pure water is already pretty small, 10 to the minus 7 molar, but we've made it even smaller because of the H+ that we've added, and Le Chatelier's principle says we shift back towards the reactant side. So this is a really good approximation. So now what can we do? We can say here, looking at our mass balance equation, that F, to good approximation, is equal to A minus, which is equal to H plus the HA concentration. So I just noticed that there was a typo in our slides. There's a plus sign here. That shouldn't be there. These should be multiplied together. So let's just keep that in mind. So what I'm going to do now is just solve this equation for HA concentration. So HA goes there. What is it? It's F minus the H plus concentration. And so now looking at our Ka expression right here, we can go in and substitute for everything and simplify our problem. So our H plus concentration, we'll just record that. Our A minus concentration, we already said that that's essentially the same as the H plus concentration. So I can write H plus again up there. And then for the denominator right here, the HA concentration, we just found that that was equal to F minus the H plus ion concentration. So we've made this approximation, which turns out to be pretty excellent. So if we wanted to, we could let X be equal to our H plus ion concentration. So in the numerator here, we have X squared, so X times X, divided by F minus X. So if we want to, we can rearrange this equation so that we have X squared is equal to, so what we're going to do is take this equation and multiply both sides of this equation by F minus X. And we'll end up with X squared equaling Ka times F minus X. Distribute the Ka through the parentheses. We get Ka times F minus Ka times F. We're going to subtract both of these from this side of the equation and move them over to the left-hand side so that we end up with X squared minus KAF plus I messed up here. So Ka times F, this is going to be Ka times X right there. So Ka distributed in here multiplies by x minus Ka times x. So we get Ka times, let me rewrite that. There's my Ka times F. That's going to be plus, let's just start over. All right, so we're subtracting these two terms from both sides. So what do we get? We get x squared minus plus, Ka times x. So why is it plus? Because we need to add a plus Kax to both sides of the equation to cancel that out. Then we have minus Kaf. That's all on the left-hand side of the equation. So all that is going to equal 0. Lo and behold, we've got another quadratic equation to solve. A is going to be equal to 1, B is going to be equal to Ka, and C is going to be equal to the negative of Ka times our formal concentration. So we can always plug these values into our quadratic equation formula and solve for x. Oftentimes we will make what's called the small x approximation. So this is yet another approximation. And this happens when we have this condition. If F is going to be much, much greater than the hydrogen ion concentration, because it's a weak acid, we're not going to get very much of that, right? So if our formal concentration is much, much greater than the H plus concentration, then F minus X is approximately equal to F. And that makes this equation even easier to solve. So we have X squared is equal to F divided by Ka, right? So if we take this equation right here, let me show you that. So Ka, according to our equation right here, is equal to x squared over F minus x. So if F minus x is approximately equal to F, then we get Ka is equal to x squared divided by F. So let's solve this equation. We multiply both sides by F. We get that x squared is equal to F times Ka. And then we can solve for x easily enough just by taking the square root of both sides of that equation. So square root of F times Ka, that quantity, the square root of that, and that will give us our X concentration. X is what? X is the H plus concentration, which we said was approximately equal to the A minus concentration. So these are all the concentrations that we know. And then knowing the H plus concentration, we can solve for the OH minus concentration, we can find the pH, we can find the POH, all that good stuff happens from all of these equations. So the next slides I will summarize that a little bit for you, but I wanted to show you another way that we could work this problem. So we could work this problem using our old friend, the Rice table. And I'll show you where that approximation comes in. So our Rice table, we write down our initial reaction, the acid dissociation reaction. So initially, before anything is dissociated, our HA concentration is just the formal concentration, F, whatever it happens to be. So before any of it has dissociated, we have 0 moles per liter of H plus in our solution. But I want to remind you that this is an approximation, because in fact we do have some H plus in our solution because of the autoionization of water. Now we can't just use 10 to the minus 7th molar here, because that's what it would be in pure water, because we're not in pure water. The H plus ion concentration is going to be different than that because of the weak acid here. So things are going to be messed up a little bit. So this is an approximation. But before any of this is dissociated, we do have 0 moles per liter of A minus. Then we're going to get some change. We don't know what that change is going to be, so we're going to call that minus X. So using the stoichiometry, we're going to get plus X moles per liter of H plus being made, and plus X moles per liter of A minus being made. Then we just add down the columns. So what's the equilibrium E line value here for the HA concentration? Well, it's just going to be the formal concentration minus X. Here for the H plus concentration, with 0 plus X is X. And for the A minus concentration, 0 plus X is X. So we substitute the equilibrium values into our equilibrium constant expression for the acid dissociation constant. So we just substitute in our E line values. So H plus concentration is X, the A minus concentration is X. What's the HA concentration? F minus X. And so that gives us the X squared minus over F minus X that we saw from before. So we're using this approximation, and that kind of builds it in there. But this is what we got using the systematic treatment of equilibrium, but making that approximation that I told you was actually a really good approximation. So when we work a weak acid problem, we can just boom, go down and sort of start with this equation. Sometimes if F is large compared to what X is going to be, and how do we know that? Well, I usually look for, is F greater than the Ka value by at least a factor of, by about a factor of 10 raised to the power 3. So 10 raised to the power 3, 10 raised to the power 2 sometimes. You want to have those different by that amount. Okay, so we'll take a look at that in an example real soon. Just as a summary, for the reaction HA, our weak acid, dissociating, we can substitute into this equation, and this will be the equation that we need to solve to find X. So we can use the quadratic equation, or we can use our small x approximation to simplify the algebra, essentially ignoring this x that's down here, and that makes the math a bit easier. So we can say that x is equal to the square root of Ka times F. Or you can use the quadratic equation to solve that, like I showed you from before. So let's do an example. So we want to find the pH of a 0.050 molar trimethyl ammonium chloride. So this is a trimethyl ammonium cation. Chloride is there. So this is an ionic compound. It's going to dissociate to give us this and chloride. Now chloride we know is the conjugate base of a very strong acid, so it has no acid-base properties. So it does not affect the pH of the solution. This guy right here, though, is the conjugate acid of trimethylamine. So trimethylamine is a base. Okay, so this is going to be the conjugate acid, though, because we've attached an H plus to that lone pair of electrons there, giving this thing an overall +1 formal charge for that nitrogen. So we want to look up the Ka value. So this is going to be weak acid, so we can treat it just like any old weak acid. This is the H part. The rest of the molecule would be A, and it dissociates to give you H plus and A minus. And so we know that the H plus concentration is going to be equal to X, and we get that by solving this equation, that Ka is equal to X squared over F minus X, where F is our formal concentration. So F is going to be our 0.050 molar here. And how do we find Ka? We need to look that up in Appendix G. And the Ka value turns out to be, assuming 0 ionic strength, ignoring activity effects, 1.59 times 10 to the negative 10th. All right, so 10 to the negative 10th tells you that this is an extremely weak acid. So we're going to get very little A minus, very little H plus. And so that tells you that this F minus X is probably going to be a good approximation, that we can say F minus X is approximately equal to F. Okay, so how did I know that? I looked at the 10 to the minus 10 number here, and I looked at this number, which is on the order of 10 to the minus 2, and I noticed that these powers of 10 are different by greater than 3 powers, right? So from minus 2 to minus 10 is way more than 3 powers of 10 different. So usually that means that this is a good approximation. So we can make that approximation and then check it. So let's just do that. So we solve for X. We're going to ignore X here. There's our small x approximation, so we ignore that. Multiply both sides by F. Take the square root of both sides. We get X, which reminder is our H plus ion concentration, is equal to the square root of 1.59 times 10 to the negative 10th times formal concentration, 0.050 molar, and we'll take the square root of that product. And I got a value of 2.8196 with way more decimal points than we need, times 10 to the negative 6th power for the molarity. Again, since we have two significant figures in our molarity here for the formal concentration, we would report this to two significant figures following our significant figure rules. Okay, so if you had used the quadratic equation to solve this, you would have gotten essentially the same result. So good news then, our small x approximation worked pretty well. Also, let's just check the small x approximation. So is it true that in fact 0.050 molar is much, much greater than 2.8 times 10 to the minus 6 molar? Is that true? Why, yes, it is. And really, we want the difference to be something less than a 5% difference. So as long as you're somewhere in there, we're probably good enough for our purposes. It certainly gets us in the ballpark. So yeah, these are much different. So our small x approximation was good. It's a good approximation. So we were asked to find the pH, so we've got one more step. Not quite done with our problem. pH is the negative log of the H+ ion concentration, ignoring activity effects, which we will continue to do for most of the rest of the chapter. So you can stop fretting about activity effects. So we're just going to take the negative log of this number, and that will give us a pH of 5.55. And so here's the worked out solution from your textbook. There's a test yourself problem down here if you wanted to try to do it for triethyl ammonium bromide. So it looks a lot like this, except we've got ethyl groups here instead of methyl groups, and we've got a bromide here instead of chloride, but that doesn't matter at all. So you'll just need to look up a different Ka value on Appendix G for triethyl ammonium. So you would look up triethylamine, which doesn't have the H on it, so that would be the neutral molecule. And then you can find the Ka for the conjugate acid species and work that problem out. So our next topic is to talk a little bit about fraction dissociation. So because these are weak acids, only a small fraction of these molecules are actually going to break apart, right? So if you got 1,000 molecules, maybe only 1 or 2 of them break apart into their ions. And we might want to know what fraction or what percentage of them actually break apart. So we call that the fraction of dissociation. We give it this symbol, the Greek letter alpha. I kind of write it like this, looks kind of like a fish when I write it. So that will be our fraction dissociation. Sometimes we even call these alpha fractions because alpha is the common symbol. So how do we define the fraction dissociated? So the fraction dissociated is going to be the amount that actually dissociated, right? So that will be the HA, divided by the total initial amount, all right? And so that's going to be the A- that we have at equilibrium plus the HA that we have at equilibrium. So that will give you the total amount of HA that we initially put into our solution, right? And that's going to be equal to our formal concentration. So you can see that from this expression. We know that HA is equal to F minus X from our previous work. And so that gives us this result, that the alpha fraction is just X. What is X? X is the H+ ion concentration, which we said was approximately equal to the A- concentration. And F is our formal concentration. So we can use this equation then to calculate the fraction dissociation. If we wanted to know the percent dissociation, that's easy enough. We just take the fraction, alpha, and we multiply it by 100 to convert that fraction into a percentage. Okay, so sometimes you'll be asked for the percentage dissociation. So that's easy. Calculate the alpha fraction using this formula and then multiply by 100. So let's do an example. What's the fraction dissociation for a 0.05 molar solution of trimethyl ammonium chloride? So this is the problem that we worked earlier. So we've already done this calculation. So just a reminder that our trimethyl ammonium chloride breaks up into trimethyl ammonium cation and the chloride anion. And then this trimethyl ammonium ion acts like a weak acid and breaks up to give you trimethylamine and H+. So we already found that work. We figured out that H+ was equal to 2.8 times 10 to the minus 6. Remember, that's what we called X. That's approximately equal to our A- concentration. So we just substitute that into our alpha fraction formula here. So 2.8 times 10 to the minus 6, our formal concentration is 0.05 molar. We plug that in, do the division, and you get an alpha fraction of this. Okay, so that's a tiny fraction. Only a very small number of the molecules that we have actually break up into ions. So for example, if we were to multiply this by 10 to the power fifth, right, then that means we would have 10 to the power fifth is 10,000, right? So if we have 10,000 of these HA molecules, about 5.6, or rounding to the nearest molecule, about 6 of those 10,000 molecules actually break up to give you these ions. So most of them, the rest of them, are going to stay together without the hydrogen ion dissociating. So if we multiply this by 10 to the fifth, cancels that out. we get 5.6. So 10 to the power 5 is 10,000 molecules, and we would only have about 6 of those molecules that actually break up. So a very small fraction of the initial weak acid exists as the conjugate base form. So it turns out that the amount of weak acid that you have in the solution is going to depend on the pH of the solution, right? And we can see that from Le Chatelier's principle. So let's imagine that we decrease the pH. So if we decrease the pH, that means we have more and more H+ ions. So according to Le Chatelier's principle, that's going to shift this equilibrium this direction. And so that means we're going to have less and less of the A- present in our solution. So it's going to dissociate less and less and less as the pH of the solution goes down. We can see that mathematically by sort of doing a little bit of algebra here. So starting with our Ka expression, we can rearrange it a little bit to give us this. And then we can go back to our alpha fraction expression right here, right? And so what we're going to do is take this expression and we're going to divide both the numerator and the whole entire denominator. We're going to divide that by A-. Okay, so A- divided by A- gives us 1. And here in the denominator, we're going to distribute that A- inside the parentheses. So we have HA divided by A- plus A- divided by A- just gives us 1 again. And so that gives us this expression. We will remember from up here that Ka divided by H plus is equal to A minus over HA. So that tells us that this bit right here, right? Well, that's just the inverse of this, right? So HA over A minus is equal to H plus over Ka. And so we can substitute in here for this bit the stuff that's on the right-hand side of this equation. And so we get this equation. And so the reason that this is useful is this shows us our H plus dependence. So as we change the pH, we're changing how much H plus is in our solution. Remember that if we know pH, that we can figure out the H plus ion concentration just by undoing the negative logarithm. So it's just going to be 10 raised to the negative pH power. So if you happen to know your pH, then you can just figure out the H plus ion concentration this way. So let's just start with this equation and imagine what conditions we would have to have present to have 50% dissociation. So 50% dissociation would be for alpha to be 0.5. So in order for alpha to be 0.5 or higher, the H plus concentration has to be the same as the Ka value. And so our H plus concentration could be no higher for the weak acid that we were working with, the trimethyl ammonium chloride, could be no higher than the Ka value for that, 1.59 times 10 to the negative 10th. So in general, the H plus concentration, in order for this to be true, would have to be less than or equal to the Ka value, because that would get you 1 here for this term if they're equal. 1 plus 1 gives you 2. 1 over 2 is 1/2. That gives you the 50%. So for our acid that we were looking at, you see that the H plus concentration has to be really, really tiny. So we would have to have a fairly basic solution in order to have a solution where we were 50% dissociated for that particular weak acid.